Hi everyone, this is Anand and today we will be discussing the problems and solution of CodeDrift. Hi everyone, so today in this video I will be discussing the problem 1 and 2. So the problem says that you are given two digits 1 and 2. Let us denote f of x as the number of permutations of an array consisting of the given digits whose sum is x, okay? And let us denote the g of s as the sum of f of x for all x from 1 to s. So g of s is basically equal to the sum over f of x where x lying between 1 to s, okay? And f of x is the number of permutations of an array consisting of only the digits 1 and 2 with sum being x. And you're also given an array of size n, okay? The array is a. You have to find a single integer which is the sum of all g of s over all the elements of the given array. Since this number can be large, print its modulo 10 to the power 9 plus 7, okay? So actually this should be equal to 10 to the power 9, okay? So so we need to calculate its modulo 10 to the power 9 plus 7. So we have to calculate what? We have to calculate the sum over all the g of s of I, or you can say g of a of I, okay? We have to calculate g of a of I and sum it over all the i's starting from 1 to n, okay? Like if the array is like a1 a2 up to an, so we have to calculate g of a1 plus g of a2 so on and so up to g of an. This is the thing we have to. Okay, so let's see what f of x denotes. So f of x is basically the number of permutations of 1 and 2 with the sum equal to x. For example, if you take x is equal to 3, then basically there are three permutations like 1 1 1, then 1 and 2, and then 2 and 1. So all of them sum up to 3, and these are like three distinct permutations, so f of 3 will be equal to 3. Similarly, for x is equal to 5, there are like these 8 permutations of 1 and 2 which sum up to the same thing, 8. So sum up to the same thing which is equal to 5. Okay, so like either all of them are ones or like 2, then the rest 3 ones. Okay, you can just choose the position of placing this 2, and that will give you 4 permutations like this, okay, with all summing up to 5. And similarly you can just fix 2 of them to be equal to 2 and the rest to be 1, and just permute in this in 3 way. So you will get 3 permutations from here, 4 permutations from here, and 1 permutation from here. So that's why f of 5 will be equal to 8. Okay, so now let us see how we can calculate f of x. So since f of x is the number of permutations of only 1 and 2 and with the sum equal to x, so now one thing you can notice is that for finding f of x, okay, either we will choose to place a 1 or we will choose to place a 2 for starting the sequence. Okay, for starting our permutations, either we will be placing 1 or 2. So what we will do, we will try to find all the permutations, or you can say the number of permutations which start with a 1 and sum up to x minus 1. Why? Because you want the total sum to be equal to x, and you are starting your permutation with 1, so the remaining must sum up to x minus 1. Okay, similarly you find how many permutations will be there which will start with 2. Okay, so if you are starting some permutation with 2, then the rest of the numbers must sum up to x minus 2. So you try to find these two things, okay, and simply sum up them together, and that will be the value of f of x. So the number of permutations of 1 and 2 such that their sum is equal to x is basically the number of permutations with sum equal to x minus 1 plus the number of permutations with sum equal to x minus 2. Okay, now this is nothing but a general equation for a Fibonacci number. So a Fibonacci number is basically a Fibonacci sequence. So in a Fibonacci sequence, the ith number is basically equal to the sum of the previous two numbers. Okay, so this is the same thing, that f of x is equal to f of x minus 1 plus f of x minus 2. So what you can do, you can just simply calculate it for every x. Okay, uh, since a of I is, okay, a of I is lesser than or equal to 10 to the power 9, so calculating the f of x, okay, for any a of I will be of the order of a of I. Okay, so this is the thing which we can just do naively. Okay, now but we don't even need to calculate f of x. Okay, we don't need to calculate f of x, we need to calculate something known as g of s. Okay, so what is g of s? So g of s is basically f of 1 plus f of 2 plus f of s. Okay, we need to calculate this thing. So even if we just calculate, or you can say if we just pre-calculate all these f values, then even then calculating g of s will surely require order of s time, right? And since we need to calculate this sum for all the values of a of I, okay, we need to calculate over all the values of a of I. So that's why calculating it naively will just require a time complexity of order of n into the time complexity for calculating g of the maximum value of a of I. Okay, so calculating g of a of I, and a of I is around 10 to the power 9. Okay, will force us to calculate f of 1 plus f of 2 up to f of 10 to the power 9. So that will be around something like this. Okay, so that will not fit in the constraints given in the problem. Okay, so because we are given ai to be equal to 10 to the power 9, right? So we should try to somehow optimize it. Okay, like can we do better? We should try of thinking of optimizing it, right? So and like moreover, calculating this f of s will like if you want to calculate something like f of x using a for loop, that will also require a time complexity of order of x. Okay, if you use that simple formula that f of x is equal to f of x minus 1 plus f of x minus 2, so calculating the f of x using that will still require order of x time. So let us see how we can optimize our approach. Okay, so let us see that. Okay, so we are writing, let's say g of, let's take for example, if s is equal to 8. So if x is equal to 8, we are calculating g of 8. So g of 8 will be equal to f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6 plus f of 7 plus f of 8, right? Now let us see one thing, that if we write g of 8 again in some other form, what we do, let's say we just, so let's say if we just pair these two things together, if we just pair these two things together, and let's say we pair these two and pair these two. So by pairing, what I mean that we can use this thing like if f of x plus f of x plus 1 is equal to f of x plus 2. Okay, basically it comes from the same fact that f of x is equal to f of x minus 1 plus f of x minus 2. So if instead of x, if you just put here x plus 2, okay, if you just simply put x plus 2, then you will get this thing, right? So now you can see that f of 1 plus f of 2 will now become equal to f of 3. Similarly, f of 3 plus f of 4 becomes f of 5, f of 5 plus f of 6 becomes f of 7, and f of 7 plus f of 8 becomes f of 9, right? Okay, so this is one way of writing your g of s. You can write g of 8 as f of 3 plus f of 5 plus f of 7 plus f of 9, right? Similarly, you can also write your g of 8 in pairings in some other way, right? So if you just, instead of pairing like this, okay, let us don't pair in this way. Okay, let me remove it completely. Okay, so we had f of 2 plus f of 3, f of 4, f of 5, f of 6 plus f of 7 plus f of 8. So this time let us pair in this way, that you pair f of 2 and 3, then 4, 5, 6, 7, and just leave over 8. So if you pair like this, what you will get, you will get f of 1 plus this will become f of 4, next will become f of 6, next will become f of 8, and then f of 8 again. Now if you just simply add these two equations, let it be 1 and let it be 2, so you will get 2 times g of 8 will be equal to what you get. You get f of 1 plus f of 3 plus f of 4 plus f of 5 plus f of 6 plus f of 7 plus f of 8 plus f of 9 plus f of 8, right? So you get something like this. Okay, now one thing you can notice is that basically you can write this thing like f of 3 till this point. So what you can write it, you can write it like this, f of 1 plus g of 8 minus f of 1 minus f of 2 plus f of 9 plus f of 8. You can write this thing like this, right? Because g of 8 was the sum over all the f from 1 to 2. So since 1 and 2 were missing here, you can write g of 8 and just subtract f of 1 and f of 2 from it. Now this will get cancelled, this and this got cancelled, and uh, g of 8 is here, so you can just shift this g of 8 to here. So 2 times g of 8 minus g of 8 becomes g of 8. So g of 8 now becomes equal to what it got, it becomes equal to f of 9 plus f of 8 minus f of 2, right? And from this you conclude that like f of 9 plus f of 8 again becomes equal to f of 10 minus f of 2. Okay, so this is the thing you got, right? This is the thing you got. Now you don't need to calculate for calculating g of 8, you don't need to just iterate from 1 to 8 and summing f of 1 plus f of 2 plus f of up to f of 8. You don't need to sum, like you don't need to iterate for 8 times. You just simply calculate f of 10 and subtract f of 2 from it. Okay, so in this way you can also generalize for any n that g of n will be equal to f of n plus 2 minus f of 2. Okay, since n is equal to 8 in this case, that's why you can also see that 10 was coming here, and you can further write it like this also, f of n plus 2 minus f of 2 which will be equal to 2. Okay, so this is the thing we got. Okay, but still you see we need to calculate somehow this f of n plus 2. So still the thing remains the same, that for calculating g of s we need to somehow calculate f of s plus 2 minus 2, and calculating this will naively will require order of s time. So how can we fasten this, how we can make it somehow faster or more optimized? So here comes the approach. We can use somehow or like something called as matrix exponentiation. So if you know it already, it's really appreciable, but if you don't know it, you can still learn in this. So you need something known as matrix exponentiation. Okay, so matrix exponentiation can be used to calculate the nth Fibonacci number in order of log n time into some constant which is generally equal to 8, right? Or you can simply say in order of log n time. Okay, so in order of log n time you can simply find the nth Fibonacci number. Okay, so now let us see how we can find the nth Fibonacci number using matrix exponentiation. So the general equation for Fibonacci number was f of n is equal to f of n minus 1 plus f of n minus 2. Okay, so what you can do, we can write it in the form of a matrix like this. So let's say we declared a matrix like this. Okay, so what we can do, we can write it like this. So f of n is equal to f of n minus 1 and f of n minus 2. Okay, so if you just put it like this 1, so obviously if you just multiply these ones with these, with this row, with this column, then you will get this thing like 1 into f of n minus 1 plus 1 into f of n minus 2 will give you f of n will give you f of n minus 1 plus f of n minus 2, which will be equal to f of n. Similarly, if you put here 1 and 0, now as you can see, if you just multiply this row with these columns, then 1 into f of n minus 1 into 0 into f of n minus 2 will be equal to f of n minus 1. Okay, so now you can see that this things holds here. Okay, so it means that you can write it like this, right? You can write things like this. So now you can see that we have represented our uh, functional equation of Fibonacci number in the form of a matrix. Okay, so let's say that if n is equal to, let's say, 4. Okay, so what you can write, you can write f of 4, then you can write f of 3. So this will be equal to 1 1 1 0, and then it will be f of 3 and f of 2. Okay, so by using the same identity, if you just write it again, you will get 1 1 1 0, and if you just again use the same recursive function again, you will get 1 1 1 0, and this thing will get reduced to f of 2 and f of 1. Okay, so you got something like 1 1 1 0 squared f of 2 and f of 1, right? Similarly, if you just use it over again, then you will get something like 1 1 1 0 to the power 3 and f of 1 and f of 0, right? So f of 1 is basically 1 only, and f of 0 is also 1 only. So when you define a Fibonacci sequence, you define for the values for 0 and 1 to be equal to 1 only. Okay, so you see that when you started with f of 4 and f of 3, right, you ended with some matrix, some constant matrix whose power is equal to 3, and then multiplied by f of 1 and f of 0. So if you generalize it for any n, then you will see that f of n, if you just simply calculate this matrix, this will be equal to this matrix raised to the power n minus 1, and that will be multiplied with f of 1 and f of 0, which are both equal to 1 in this case. Okay, so what we can do, we can just calculate the power of this matrix. Okay, and let's say after calculating the power of this matrix, it looks something like this: x1 x2 x3 x4 1 1. Okay, now if you just multiply them together, you will get something like x1 plus x2 and x3 plus x4. Since we are just interested in the first element, so f of n will be equal to x1 plus x2. Okay, so what it means is that we will just simply calculate what will be the value of this matrix, like this matrix, which is 1 1 1 0 raised to the power n minus 1. We will find this matrix, and we will just sum the upper two, like the values present in this upper row. Okay, and by summing them together, we will get our f of n. Okay, so calculating the power of a matrix. So now there comes the question of calculating the power of a matrix. power of a matrix. Given a matrix x, let's say this x was this, how can we calculate x to the power some number n? Okay, so one way of multiplying the matrices or finding the nth power of a matrix x is to like write x to the power n like this, x into x into x around n times. Now what you do, you first multiply these two matrices. Okay, after multiplying these two matrices, let's say you store it in some matrix y, or you can say you got a matrix y. Now you multiply the matrix y and x again. Okay, whatever resultant matrix you got, you again multiply it with x. Okay, and just keep on doing this. So basically what it means is that you multiply around n minus 1 times two matrices of size 2 cross 2. Okay, so we are basically multiplying n minus 1 times two matrices of size 2 cross 2. Now multiplying two matrices of size 2 cross 2 will actually be an order of 8 operation, basically order of m cube operations, where m is the order of the matrix. So since it's a square matrix, it will be of the order of 8. Okay, so doing it for n minus 1 times, there are basically n minus 1 multiplications, so that will give you order of 8 into n time complexity. So this is the time complexity if you find the matrix the exponent of the matrix in this way. Now let us think if we can optimize it or not. So for optimizing it, what we can do is we can just use somewhat, or you can say something similar to binary exponentiation, because you see that the only difference uh, in x here is that instead of x being an integer, here x is a matrix. Okay, so in binary exponentiation x used to be an integer. Okay, and in a matrix exponentiation x will be a matrix. Okay, so similar to binary exponentiation, we can use metric exponentiation. The only thing which will differ is that the way we will be multiplying two matrices. So in integers, we used to multiply simply by putting a into sign between these two variables. Let's say if we are multiplying two things, x and y, we simply say x into y. But for multiplying two matrices, we need to follow the standard procedure for multiplying two matrices. Like we multiply all the elements in the first row with the elements in the first column. Okay, so that becomes our element for the resultant matrix first cell. Similarly, we multiply the second row with the we first row with similarly we then multiply our first row with our second column, then third column, and we just keep on filling. Okay, so we can just do that in that way. So similar to binary exponentiation, if we use matrix exponentiation, then we will get a time complexity of order of log n into the order of multiplying two matrices, which is 8 in our case. So we will get a time complexity of order of 8 into log n in that case. Okay. Okay, so now let us look at the pseudocode for it. So let's say this is a function find, which will be accepting an array of size n. So we declared a variable answer, initialize it with 0. We just iterated over for every element s in a. We calculated g of s. Okay, and we now know that g of n will be equal to f of n plus 2 minus 2. So it should be s plus 2. Okay, so this will be equal to g of s will be equal to f of s plus 2 minus 2, and g of s, we just taken its modulo with 10 to the power 9 plus 7, and after that we added the value of g of s to our answer, and we will also take its modulo with 10 to the power 9 plus 7. Okay, and at the end, after doing it for all the elements in the array, we will simply return our answer. So here we are using a function for calculating the nth Fibonacci number, which is f. So let us see the implementation of f. Okay, so let us see how we are implementing the finding the nth Fibonacci number function. So we initially had a matrix x. X is initially equal to 1 1 1 0. Now as we derived earlier that like the value of this matrix, basically if you f of n and f of n minus 1, this matrix is basically equal to this matrix raised to the power n minus 1 and then 1 1. Okay, these were basically f of 1 and f of 0. So we need to find the n minus 1th power of this matrix. So what we can do, we can simply find the power of x raised to power n minus 1. Okay, so we just decremented n by 1 because we need to find the n minus 1th power of this matrix. So we decreased our n by 1. Now we declared a matrix, answer matrix. So initially it will be an identity matrix. Now we will be just doing the traditional or like iterative binary exponentiation kind of thing, that while n is not equal to 0, we check if n is divisible by 2 or not. If it is divisible by 2, then we simply update our answer matrix equal to multiplication of answer matrix and x. Okay, and then we say that x is equal to multiplication of x into x, and after that we just simply divide our n by 2, and at the end we just return the sum of the first two elements of the resultant matrix, okay, and take n modulo 10 to the power 9 plus 7, because as you would have seen that in the solution with that we derived that f of n is basically equal to x1 plus x2, okay. So here as you can see that f of n, that the nth Fibonacci number is basically equal to x1 plus x2. X1 and x2 are the first row elements in the resultant matrix, okay, like this matrix raised to the power n minus 1. If you got a matrix, resultant matrix like this, then you simply find the sum of the first row elements, okay. So that's why here we are doing that. Okay, here we are just adding those two elements and finally returning. Let us see the code for pseudocode for multiplying two matrices. So given two matrices x and y, we declared a matrix z of size 2 cross 2, then for each I from 0 to 1 and for each j from 0 to 1, basically we are declaring a variable sum over here, and using this sum we will just calculate the value of z of ij, okay. We iterated for k is equal to 0 till 1, so sum plus is equal to x of ik into y of kj. We taken its modulo with 10 to the power 9 plus 7 and simply equated z of ij is equal to sum, and finally return the final matrix z, okay. So as I discussed earlier also that the time complexity of this will be order of, okay, I discussed earlier also that the time complexity of this solution will be order of n log of, like, whatever is the maximum value of ai, okay. This will be the time complexity because since g of a of I is equal to f of a of I plus 2 minus 2, now calculating this thing will require log of this thing. So whatever is the maximum value of a of I, log of that thing, and since there are n elements, multiplying it by n. Now the space complexity, basically the extra space complexity of this will be equal to order of 1, because we are not using any extra space other than for storing the result of multiplication of two matrices here, okay. We are declaring a matrix z of size 2 cross 2, and also over here we are using a answer matrix also of size 2 cross 2. So but still, like, that only requires the storage space of order of 4, so we can consider that as being order of 1. So that's why the space complexity will be order of 1, and the time complexity will be order of n into log of maximum value of ai. And you can also add one more factor, 8, because multiplying two matrices of size 2 cross 2 will give you a time complexity of order of 8. So the final time complexity will be 8 into n into log of maximum value of ai, okay. So I hope it's clear to you. So if you enjoyed the video, please like, share and subscribe our channel. Thank you.